Hi everyone. Today we will introduce the notion of variance of a random variable, a central notion in probability and statistics. But first, let's recall the basic concepts. A random variable x is a real valued function on a sample space. Random variable x takes an outcome of the experiment, for example, a sequence of coin flips, and outputs a number, for instance, the number of heads in that sequence of coin flips. If x takes values x1, x2, x3, and so on, with probabilities p1, p2, p3, and so on, the expected value of x, also called expectation or mean, is computed by multiplying every value by the corresponding probability and then summing overall values. So a random variable transforms an outcome into a real number. Sometimes you want to further transform it using some other function g, for instance, square the number of heads or subtract 5 from that number of heads. So generally, if we have any function g, when you first apply x and then you apply g, is also a random variable. What values does it take? Whenever x takes value xi, g of x takes value g of xi, with the same probabilities. So expected value of g of x can, by definition, be computed by multiplying each value by the corresponding probability and then summing overall values. So for instance, the expected value of x squared is computed by squaring each value of x, then multiplying by the original probability and summing overall values. We are ready to introduce the concept of variance of a random variable. A random variable x generally can take many values, but there is one value that represents it's the best. It's the expected value. It's kind of a center of the random variable. If the expected value is the center, we would also like to know how much the values of the random variable deviate from that center. What is the variability in the values that the random variable x can take? That variability, that deviation, is captured by the concept of variance. It's supposed to quantify how much a random variable deviates on average from its expected value or mean. Let's call the mean mu. So let's take x, subtract the mean. That will quantify the deviation of x from its mean. It could be positive if x is larger than mu, could be negative if x is smaller than mu. We would like the notion of deviation to be always positive. It's supposed to capture the distance the true value of x is from its expected value. So it's going to be non-negative. To make it non-negative, we can just take absolute value. To capture the average deviation, we can take the expected value. We defined the expected absolute deviation of x from its mean. Unfortunately, this expression is inconvenient to work with. It's hard to compute. Remember the definition of absolute value. It's a for positive a and minus a for negative a. So the absolute value breaks down into two cases. Now suppose the random variable x can take hundreds of values, x1, x2, and so on and so forth. For each value, you'll have two cases. So you'll have to break down 100 values each into two cases, and that becomes 2 to the power of 100 cases. Impossible. This expression will be very difficult to compute. So a reasonable attempt, but the result is very inconvenient. How can we do this better? The problem was that the absolute value was inconvenient. So let's replace absolute value with something else. Why in the first place we even talked about absolute value? Well, we wanted to kill the sign. What else? What other function can effectively kill the sign? Yeah, square. Instead of taking the absolute value, let's square the deviation and take the expected value. And that quantity is called the variance of x. It's denoted like this. Almost perfect. But there is one little thing that's still not right. Squaring messes up the units. For example, if the random variable x measures our belief about the age of a fossil in years, then squaring that will measure deviation in years squared. That doesn't make any sense. It should be years. So how do we correct this? By taking the square root back. So once we compute the variance, we can take the square root of it, get back to the original units, and the result is called the standard deviation of x, usually denoted by sigma of x, and computed by taking the square root of the variance of x. The standard deviation is easier to interpret, and variance is easier to compute. Let's check. Let's expand this square and see what happens. We get x squared minus 2x mu plus mu squared. Then we use linearity to break the expected value of the sum of three terms into the sum of expected values. Now 2 and mu are constants. So again, by linearity, we can pull them out of the expectation. Mu squared is a constant, and the expectation of a constant random variable, the random variable that always takes the same value, mu squared, is that value, mu squared. Expected value of x is what we called mu in the first place. And so here we subtract 2 mu squared, and we add back 1 mu squared. So the result is expected value of x squared minus mu squared. And then recall what mu is again, and we get this alternative formula to compute the variance. So to compute the variance, you take the expected value of x squared, then you take expected value of x and then square it. And surprisingly, these two numbers need not be the same. Otherwise, variance would always be 0, and it is not. So to summarize, we defined variance this way. To interpret it, we take the square root and get the standard deviation of x. It measures the average dispersion or average deviation of x from its mean. Now, to compute the variance, sometimes you would want to use the formula in the definition. At other times, this alternative formula can be more helpful. And now let's practice. Let's compare the following two investment options. Let's decide which of these two imaginary stocks is better, stock A or stock B. Suppose stock A yields 3% return with probability 0.8, but 2% loss with probability 0.2. Stock B yields 5% return with probability 0.6, but 2% loss with probability 0.4. How do we compare these? Let's compute the expected return in each stock and see which is larger. Let's call return XA for stock A and XB for stock B. These are random variables because we can't see the future. Now, return for stock A, XA, takes value 3% with probability 0.8 and minus 2 with probability 0.2. So to compute the expected value, we multiply the value times probability, another value times probability, and sum. And we get 2%. Similarly, for stock B, we multiply this value, 5, by this probability, then this value minus 2 because of the loss with this probability, and sum. And we get 2.2%. So we expect stock B to yield slightly better return than stock A. Is the expected return the only metric that we would like to look at? There is another thing, the risk. We should compare the risks of investment into stock A and stock B. To quantify the risk, we want to look at the variance, at how much the true return on average deviates from its expected return in each case. To compute the variance of XA and XB, this formula is helpful. Why? Because we have already computed the expected values. The only thing that we need to compute is the expected value of the square. Let's do it. The square of a random variable, the square of the return, takes value 3 squared with probability 0.8 and minus 2 all squared with probability 0.2. So expectation is then 3 squared. times 0.8 plus minus 2 squared 0.2, and we get 8. And similarly, the square of the return of stock B takes value 5 squared with probability 0.6 and minus 2 all squared with probability 0.4. And we get 16.6. So according to this formula, the variance of XA is this number minus this number squared, which is 4. And similarly, the variance of XB, according to this formula, is this number minus this number squared, which is 11.8. To interpret these numbers, let's take the square root of them and get the standard deviations. And we get 2 and 3.4 respectively. So we can intuitively interpret the result of our solution as follows. Stock A on average yields 2%, but typically deviates from this value by 2% on each side. And stock B on average yields 2.2%, but typically deviates from that value by 3.4% on each side. So now we have more information to compare these two stocks. We should expect approximately the same return from both of these stocks, but the risk of investing in stock B is much higher. So I don't know about you, but I would probably invest in stock A. We'll keep practicing with the notion of variance in the next episode. Stay with me.